In this video, we are going to be taking a look at a master boot record of a FAT32 partition. So this is probably the dullest thing that you may ever see, but it was actually quite enlightening, and I figured I would show that here. So what you're looking at right now is the boot sector, or sector 0, of a FAT32 boot drive. So what I did is went online and downloaded a very small version of Linux. And then after I downloaded that version of Linux, I used Rufus, which is a bootable USB creator software. And I loaded that operating system and burned it onto a 32 gigabyte flash drive. So after I burned the flash drive, I opened the raw sectors in HXD. HXD is a very nice software that you can use to view contents of your various disk drives and files. And then I dumped out the first sector. So I'm going to go ahead and plug in the USB right now. And you can see here, I've enabled hidden files here so that we can see what's going on. Go to Tools, Open Disk, and select your disk. And now you can see a complete hex dump of all of the sectors on your flash drive. Okay, so the first thing to note is that just by looking here, we can see that there's the OEM ID, in this case it's SysLinux, as well as the format of the drive, which is FAT32. There are a couple of other strings that we can see. For example, no name here, and boot error down here. Beyond the 0 sector, there's not much. We do see in sector 6 and MS-DOS 5.0 boot sector, and it is a valid boot sector because of the 55AA signature, but nothing else down here. Sector 12 does contain some more as well. And this actually is the default code. We see this for a drive formatted without any operating system. Okay, you'll see a branch to, I believe, this address in that case. But we do have an operating system on here, so let's go ahead and reverse it. So I've already dumped the code in IDA and obviously made some comments already, but most importantly, I want to bring attention to the BIOS parameter block, in particular the extended BIOS parameter block. So here we can see a couple of entries that I've already labeled, but again, these are all taken from the wonderful Wikipedia page where you can learn all about the different fields in this block. So for example, we have the OEM, we have bytes per sector, which is usually going to be hex 200 or 512. We have sectors per cluster, which is usually, well, it depends on your allocation unit, but in this case, in the default value of 16 kilobytes, it's going to be 32 sectors per cluster. The reserved sectors is interesting because it is the number of sectors that go before the first actual file allocation table in the FAT file system. So in this case, we have AE0, which is 2784 reserved sectors, the first of which we're looking at right now. The entry and offset hex 10 is the number of file allocation tables. In this case, we have 2. We have the description of the media at offset hex 15, sectors per track at offset hex 18, which is not actually used these days because this is not a floppy. Similarly with heads. Hidden sectors is also an interesting field because it is labeled as 800, even though really this means that there are no hidden sectors. This is just for alignment to 2048. Initially on earlier DOS systems, this value was 63. But again, due to alignment, it is now 2048. Here's the total sectors count for our disk. We can see that it is quite a large number, about 61.5 million sectors, each sector, of course, with 512 bytes. So that comes out to about 32 gigabytes. Here we have the sectors per file allocation table, and this is a pretty standard value. And we have the root directory cluster, which is the cluster containing the root directory. In this case, it's 2, which is a very typical value. We have the FS information sector, the copy boot, or the sector that contains the copy of our boot record. And the physical drive number, which in this case is preset to 80, but it will be modified as we go through our code. So let's go ahead and get started at start. First thing is the jump, which is very typical because it has to jump over the BIOS parameter block. And once we get to our target, the first thing we do is disable interrupts, and then we clear the directions block. In other words, we're going to copy towards higher memory. This is the, I guess, the direction that makes sense. Usually, you should not rely on the BIOS to give you the direction flag in the correct configuration. So this is a good practice. Then we XOR CX with CX, basically making it 0, and then initialize that SS here with CX. So the stack segment now will be 0. We're going to move 7B76 into SP and then push all of these values. And because we know the value of SP, we also know the addresses of these saved values, which are listed here. We then set the extra segment to 0. We move hex 26 or 38 into CL, which is a count of the number of words that we're going to copy down here. And then we're going to move the destination index register. We're going to set that to 7B78. So as you can see, it is going to be just above our saved values here. And then we're going to rep mobs W, which is going to copy from SI. Now you may be wondering why we haven't really initialized SI here, and BIOS usually does not give us the value of SI pointing to something meaningful. But in fact, because this is syslinux, as you can see by the signature, because this is syslinux, there is actually a very specific format or a very specific procedure in order to pass code from the PMBR or from the BIOS to the PMBR boot code. And that is here explained very well on this page. And we can see that what happens is we are passed a structure here, and in fact this is also available on the master boot record page, I believe. Do it partition table. You can see right here. So DSSI actually does point to a value. It points to the hybrid MBR handover structure, which contains a MBR partition, a dummy MBR partition table. Okay, so that is actually a partition table that we are passed. Okay, cool. So we copy the values over, and then we are going to move BX. We're going to move FS at BX into SI, which I'm not really sure what that value is. And then we push that value. Then we check DL. So remember, DL is initialized with the drive number, which is almost always going to be the case. And so then we check the sign, right? And if there's a sign, then we go over here. Otherwise, we're going to go down here. Okay. So, but in either case, it's just checking for whether or not this is a bootable hard drive or if it's a floppy. Right. So then if we go over here, we perform some additional checks, and this essentially determines whether we're going to use one of these three conditions. One of them is we're just going to use the hidden sectors as our offset. Another one is we're going to use the partition start LBA here. If the magic number doesn't check out, but we do have a certain configuration here. It's the 128th floppy, and the partition type is MBR. Otherwise, we're going to use this special value. And again, these come from the structure that we're passed in the DSSI registers. Okay. But it's not too important because assuming that we're booting from just a standard BIOS, right, we're probably going to end up in this block over here. In other words, we're just going to load the hidden sectors, which in this case is X800. So after arriving down here, we join back down. We now enable interrupts, and then we make a call to int13. As you can see, this is just a small wrapper around that with AH equals to 41. And this is to check if drive extensions are present. Again, Wikipedia is a wonderful resource to find out all about these interrupt calls. So we can see here, this is to check if drive extensions are present. We need PX to be 55AA. And we need DL to be the drive index, which in this case it obviously is. We haven't really changed that. So then we check the result of that. B, if B jump up below, so that will check the carry flag. If the carry flag is set, that means that the extensions are not available. In this case, we jump over all this code here. If they are available, we do some additional checks. We first check if the return value in BX is AA55. This is basically a hard-coded return value that we can just check if the function returned properly or executed properly. And then we go down here, test if CL against 1. And you can see testing against the bit mask 1 checks if we can use the packet structure to access the device. And if that is also 0, or if that is not 0, in other words, if the test returns true, then we move 0 into this weird location, 7045 plus 1. Now this is very strange, but if we actually go and see what's going on, we follow the link here, we can see that this location is here. And going to the hex view, we can see that this is a 2-byte jump instruction. So if we move 0 into that address, what we're essentially doing is saying we're not going to take the jump at all, we're just going to continue on with the next instruction. So this is essentially some crazy voodoo self-modifying code business that's actually kind of cool, because now instead of jumping to here, if we go to the text, we're actually going to jump to here. And you can see that it actually mapped the same general location, we're just now up here instead of down here. So this is actually going to jump to here. It's not actually going to jump at all, it's just going to, well, just continue to the next instruction, because jump of 0 is basically a no-hop instruction. So here we can see that we use int13 again, but we're going to use int13 with argument for x42, which is interesting because this is an extended read, and of course this only happens if drive extensions are present, which is exactly what the code should do. So in that case, we're going to read one sector. We're going to read it to ESBX, and we're going to read the sector given by EDX EAX. Okay, and then of course we're going to check for some errors down here. And if there are no errors, then we're going to return. Otherwise, we're going to reset the disk and then try again. And if that runs out, then we're going to go down here, and we're actually going to replace the self-modifying code so that it does jump down here properly the next time. And then we perform this sequence down here. Okay, so after we read that segment, we're going to read into segment 8000, and we're going to read from 8020, sector 8020. Now, because this value is so big, this should have you wondering whether or not this is actually still in the boot sector. So to check that, we can first see where the file allocation table starts. So hex A0 is obviously, that's the end of the reserved sectors, and we can see that's clearly less than 8020. But what about the file allocation tables? Well, we know that the file allocation table, there are two of them, right? The number of file allocation tables is 2. And we know that each file allocation table has size of 3A90. So if we do that, we can see that the data section starts at exactly hex 8000, which is pretty typical. So the fact that this is 8020 means that this is actually read from the data section. And in particular, because we know the cluster size is exactly hex 20, this is read from the first cluster right after the data section starts. So this is actually cluster 3. It's the cluster right after the root directory table. Okay, so this is an interesting thing here. We're actually reading from essentially a file, right? There must exist a file in the file system that has this sector. Okay, so we're going to read that to hex 8000 and call that, and then we're going to check a value here. So this is essentially just doing a check. If it checks out, then we're going to go here. Otherwise, we're going to jump to error. Now, error is not too interesting to look at, but we can analyze it very quickly. So what error does is it's going to move a value into SI. In this case, it's going to reboot error, and then it's going to print that message out for us. Okay, so this is something that we commonly see. If there's no valid bootable disk, we see some boot error. And yeah, so here we see 2 interrupt calls here, or actually 3. We have int10. Int10 is just a print. Okay. Int16 is going to wait for a keyboard press or wait for keyboard input. And int19 is just going to try the boot process all over again. Okay, so that's what this part does. Now, in the case that we did succeed here and the value is correct, then we're going to jump to 8030. Okay, so what is this mysterious file here at 8020? Well, to figure that out, we can open again hex edit. We can again go to our disk. And first, we're going to go to hex 8000, which is the sector that starts the data section, or in other words, it's the root directory. Okay, so we can see that sector 32768. So let's go to that sector. And we can see this is a pretty classically formatted root directory. We have all of our subdirectories here, right? And if we go and open our drive here, we can see clearly that it matches up with what we expect. So for example, we have a folder, or we have a file called ld-linux-sys, and we can indeed see there's ld-linux-sys there. After that, we have, well, here, I mean, we have a folder named, no, actually, this is not the folder. This is, I think this is just the name, but we have like system volume information file down here. We have a boot folder here, and so on and so forth. So remember, each file allocation table entry, directory entry is 32 bytes long, and it contains information about the cluster in which the file starts, the name. In this case, we can see we have one example of a long file name, in which case it got broken down into multiple entries. Okay, and as well as file size and so on. So this is the file system that we're looking at. Okay, cool. So let's see which one of these files, or if there even is one, that starts in cluster 3. So starting here with ld-linux-sys, we can see that indeed, by looking at, this is the high part, and there's the low part of the cluster number, we can see that ld-linux-sys is indeed the file that gets loaded into hex 8000. So that is the file that gets mapped to address hex 8000. If we're going to analyze it, we better load it up into IDA. So what I've done is copied ld-linux-sys to my desktop, and now I'm going to load that into IDA. So let's open a new instance of IDA. Let's go, and we're going to open from desktop, and we're going to open lvlinux.sys. Okay, and we're just going to open it as a binary file and 16-bit mode. Okay, so now you can see this is our file. Obviously, it doesn't make a lot of sense at first, but looking at the hex view, you can see again the signature SysLinux here, 4.07. And if you'll notice from the original bootloader here, it jumps to 8030, but because, well, actually, the first thing we should do is rebase this program so that we can actually make sense of some of these addresses. So 3000 is the base. Now you can see we've properly done it. And now we're going to go to, let's first of all undefine all this stuff. Okay, let's go to hex 30. So here we go. Here's hex 30, and let's make that into code. Okay, so immediately you see some stuff jump out. Let's make this a procedure and go in. So we can see now there is a lot of stuff happening. In this video, that's all I wanted to do is just kind of open up and see how the master boot record loads the file that kind of boots the operating system. This is the file that loads the operating system for this very tiny operating system. We're obviously not going to be able to reverse all this. It's a very big executable. But yeah, it's very interesting kind of to see how the operating system can be basically put on a flash drive and formatted in the specific FAT32 file system, and how it is able to load in a file that's actually in the file system and then map it into the memory and jump to it to load our operating system. So I hope you enjoyed, and I will see you in the next video.